Okay, so I'm hoping that most of this is review for you. But we are going to define what an ionic bond is and talk about when those occur. And you guys we're going to talk about how to predict the formula of the ionic bond. We're going to talk about ionic lattice and lattice energy. And we're going to describe what a molecule is and give examples. We're going to be able to draw covalent bonds and predict when this type of bond will occur. We're going to be able to count valence electrons owned by each atom. Now, I'm guessing that isn't something you guys have done before, but when you have a covalent bond, you surely already learned that they aren't equally shared, and that one atom typically gets a bigger percentage of the real estate than the other. So that's what we're going to talk about when it says that. We're going to draw our Lewis dot diagrams for atoms with molecules and single and multiple bonds. We're going to talk about resonance forms. And we're going to draw dot diagrams for molecules that have an electron deficit and that possess expanded octets. We're going to define electronegativity and talk about its periodic trend. We're going to describe bond polarity. We're going to predict if a bond will be covalent, polar covalent, or ionic. Did you guys learn polar covalent in your in honors? Where we talked about like water is polar covalent, how it has a positive and a negative end. Yeah, I figured. Name and give formulas for binary ionic compounds. Talk about compounds with transition metals, binary covalent compounds. Name and give formulas for compounds possessing atomic ions, and name and give formulas for acids. Did you guys do acid naming last year? I'm not a fan. We can't skip it. I'm sorry. I'm not in charge. All right, so let's talk first about chemical bonding overview. Basically, this is from Honors Chem. You guys know this already. You know that when they have a sharing of electrons, if an atom has one valence electron in its outer shell and the other has another valence electron in its outer shell, and they put them together and they share them, what type of bond does this form? Ionic or covalent? Covalent. Good job. And the other type of bonding is the actual transfer of electron, where one atom gives the electron to the other atom. One has a positive ion and one forms a negative ion. And what kind of bonding do we have here? Ionic. Now, so imagine that. Let's just talk about like how that's going to work real fast. Here, Abby, bring your book bag and come up here. Like that. Yep. All right, so Abby's backpack has 2 straps on the back of it, right? We're going to pretend that each of those straps is an electron. If I hold one strap and she holds one strap, now we have a covalent bond. We are sharing the weight of the backpack. If I say, you know, I don't really want your backpack, here you go. Now, I don't have any electrons. Abby has the whole thing. This is ionic bonding. That's as simple as it gets. The sharing of the electrons is covalent, and the ionic is the giving. You're good. All right? So that is basically how, and you guys know, I'm sure, that there are exceptions to every rule. But when we are talking about ionic and covalent bonding, ionic is definitely the transfer of the electrons. Oh, see? I don't know that this is going to work. And covalent is the giving. I don't know. It doesn't like me. Press the screen to start. I did practice, I swear. My husband was like, "What are you doing?" Don't worry about me. I'm working on this. I also screwed this up and I can't fix it. I don't know what I did when I was practicing, but I did. I messed it up. All right, so ionic bonding, the trends in electron motion. Here's the trend. This isn't always the answer, but it is definitely the trend. Remembering that a trend means this is typically what happens. So a metal tends to lose an electron, and a non-metal tends to gain an electron. So we see in this example, you have sodium chloride here. Sodium has one valence electron. Remembering the octet rule, sodium wants to lose that electron. So it gives that electron to chlorine. And when it does, it becomes a positive ion. Chlorine gains that electron, and then it becomes a chlorine with 8 electrons. So it also satisfies the octet rule, but now it has a negative charge. So remembering that the bond is forming when there is a positive charge and a negative charge, they are attracted to each other, and that's what forms the bonds and the transfer of the electrons. The ions typically stack on top of each other with the negative next to the positive. Remember, it's just like magnets. When you try to put two together and they like start to repel each other, they have to be opposite. Opposites attract. So it's going to go negative, positive, and they stick together. And this sticking together, this is called electrostatic attraction. Electrostatic attraction. So that combining is of the negative and positive. If you see this diagram and it has like all the positives lined up and all the negatives lined up like in a row, you know that that is not right. It is only going to work when they stack in this way. All right, so ionic bonding typically happens in 3 different ways. Has 3 different lattice types. So it has a crystalline lattice type. This is like what we see if you ever get rock candy at the store and you see it comes in the crystals. That is the crystalline lattice type where it lines up pretty and it makes these beautiful little crystals. Polycrystalline is just multiple crystals together. And then we have the, I can't remember how you say that, amorphous, which just means that there is no order in the extended structure. So the crystalline is a material with a long-range, highly ordered lattice, and the amorphous is no overall order in the overall structure. They are still negative and positive beside each other. It's not that the amorphous like mixes it up. They still are negative and positive, but they're more just like a hodgepodge put together there instead of nicely lined up like the crystalline structure. Now, one of these is more stable or has a higher intermolecular attraction than the other. Which would you imagine is the more stable of the two? Yes, the crystalline structure is a more stable of the two, meaning that it has a higher melting point and it is more likely has a higher attraction between the molecules. Okay, so that energy that holds that lattice together is called a lattice energy. And that is the amount of energy required to convert 1 mole of an ionic solid to the same amount of ions in the gas phase. So like if this is our solid here, and it's going to go to gas, oops. The question is, how much energy is that going to take? Right? So to go from a solid, neatly ordered, beautiful ion lattice structure to a randomly ordered gas. You can also see, now the solids are held together, and it does have, even though it is a solid, it still has a little bit of movement. But you guys also know that when it goes to the gas phase, it has a lot more movement and a lot more space. That's going to require energy to be able to put it into that phase. So the example we used earlier was the I think I'm out on this. All right. Let me find my clicker. So the example that we used earlier was the sodium chloride. And if you look at sodium chloride and you can see here in this chemical equation that you have, you've got sodium chloride in the solid to go to sodium ion gas plus chlorine ion gas. How much energy is that going to take? So the lattice energy, that's what we call the lattice energy. It's how much is it going to take to break that apart into the separate ions. In this example, it's 787 kilojoules per mole. The greater the lattice energy, the more stable the ionic compound is. So if we had a lattice energy that was, let's say, 1,000 kilojoules per mole, it would be more stable. If we have one that has 500 kilojoules per mole, that would be a less stable lattice. So what is holding those little molecules together is the electrostatic attraction, or the intermolecular forces, all right? And Coulomb's law is where we get this number for the lattice energy. And it talks about, Coulomb's law is the force equals K times Q1 over Q2 divided by R2. So Q1 is the charge on one of the ions. Q2 is the charge on the other ion, and R is the radius, or how far apart those two ions are in the lattice. Now, the electrostatic force F, when it is negative, that means they're attracted, and that just makes sense, because think about that. If you take Q1 times Q2, so if you take a negative times a positive, you're always going to get a negative, right? And you guys know that a negative and a positive attract. So anytime you get a negative number, you're going to have an attractive force. The opposite is also true. If you had two negatives, they're going to repel each other. If you had two positives, they're going to repel each other. So negative times negative gives you a positive number. Positive times positive gives you a positive number. That tells you that anytime your force is positive, they are repelling each other, or they are not wanting to be together. Does that make sense to you guys? So a negative and a positive are going to be an attractive force. Two negatives or two positives are going to be a repulsive force. Typically, the radius is going to be larger on our repulsive force also. So when the value of F is positive, that tells you attract or repel. Repel. Good job. When the value of F is negative, that tells you attract. That's right. Good job. So the radius can be measured using the electromagnetic microscopes that we have. It's not something that you guys will be measuring on your own using a protractor or anything like that. But you should be able to know what the negative and positive numbers are, and K is a constant. We're not going to go through any of those like equations, but you do need to know that why the force is attractive when it's negative and why it's repulsive when it is positive. And I hope that makes sense to you guys. All right, so here are two different ions, and we're going to talk about the effect of the ionic size on lattice energy. You guys know that different ions are different size based on the number of electrons that they have. And you know what the trend is on the periodic table, that ions get larger. They start small at the bottom and they get larger as they go down. So if we look at these two ions, we have fluorine and bromine, both with a negative charge. They are both in group 7A. So fluorine is at the top, bromine is at the bottom, and it just makes sense that bromine is a larger ion because it has 36 electrons in the ion form, and fluorine only has 10, right? So the ionic size increases as we go down the group. So the top of the group has a smaller ionic size, and as we go down the group, that ionic size increases or gets larger. The attraction between the anion and the cation decreases. Why? Why do you suppose it decreases? Well, let's think about fluorine. It has 7 valence electrons, right? But if we draw it as the Bohr model, let's draw fluorine. We've got 2 in the inner and then 7. Right? It looks like that. Now, if we look at bromine, got 35, right? So it's going to have 2 in the first, then 8. That's 10. Now another 8. The Bohr model doesn't actually work very well for this because now we're getting big enough that we've got 1s2, 2s2, 2p6, 3s2, 3p6. We're going to move over and we've got one more. 10, 18. You guys know that on the N3 level we actually have 18, but we're just going to 10, 18, 26. Bromine is 35. All right. This isn't very accurate, but we'll go with it like this. All right, so it looks like this. You can see when we have 2 different sizes, right? Now, think about your positives are right here in the middle, right? Here's where our positive ions are. Is it going to be easier for fluorine to pull an electron away? Because this electron shell is closer to the middle where the positives are. Whereas bromine has like all of these shielding electrons. And it's harder for it to fill the shell because it has less of a pull. Does that make sense to you guys? Yeah. So as the attraction between the ion and cation decreases as it goes down, because that positive middle is farther away from the outside and it's harder to pull it away. So the ones at the top, like your fluorine, your oxygen, your nitrogen, those are going to have a higher attraction than the ions as you move down. Also, we have a decrease in lattice energy as we move smoothly down a group for the exact same reason. Because the attraction in a lattice is a positive and a negative attracted to each other, when those ions become bigger and bigger, it's harder to get to those attractive forces on the inside of the ion. So, making sure that you understand what our trends look like, our ion size is going to increase as we go down, which hopefully makes common sense to you. And your attraction is going to decrease. So as your size increases, your attraction is going to decrease. Same with your lattice energy. Okay, now let's talk about the electrostatic force. So as the charge of the ion increases, the electrostatic force increases. For example, sodium and chlorine has 787 kilojoules per mole. If we look at, oh, that says magnesium. I was like, I don't think there is anything that is labeled in a momentary table. Magnesium with 2 chlorines, we have 3,795 kilojoules per mole. So the more the charge increases, the higher your lattice increases. Basically, the more charges you have in there, the harder it's going to be to break those charges apart. So the higher, as the charge of the ion increases, the electrostatic force increases. Holding those together is going to increase higher and higher. So the increase in lattice energy with an increase in the multitude of charges. The more charges you have, the more lattice energy you have. The more charges you have, the higher your electrostatic force. Hopefully that makes sense to you guys. All right, so you aren't expected to memorize this, but you are expected to be able to read a chart like this. Here is an example of a lattice energy chart. And it starts with, if you have a lithium ion and you combine that with a chlorine, your lattice energy is 1,036. If you combine with a bromine, you combine with an iodine.
The 40 is on the left side of the line.
Oh, I see. What happened to this chart? The chart's almost. Does it look like that on your side? No. Oh, it's only mine that's messed up. All right. So lithium fluoride is 1,036. The chlorine is 800. There you go. So we're off a little bit. Same thing for sodium. potassium, rubidium, and cesium. But you can see that your lattice energy, if you look at your group 1 or your metals, as the ion goes down the chart, the energy decreases. What we just talked about. As the ion, and it is a continuous trend that you should be able to see that it decreases for each of the types of elements. And then, oops, nope, I'm way off. Right here. So, and then when we talked about the electrostatic force or the increase in the multitude of charges, that's what this is looking at down here. If you just have a positive and a negative charge, you have a 900 kilojoules per mole. You have a positive and a negative 2 charge, you have a higher lattice energy. That lattice energy is going to increase as your number of charges increase. You can see that when you have 1 positive and 1 negative, you have 900. If you have 2 positives and a negative, it goes up. And 2 positives and 2 negatives is even higher. Same trend that you can see right here on your aluminum. You have 3 positives, your energy increases. 3 positives and 2 negatives, it increases even more. Now, you can see also that these don't, like, you can see the trend, but it's not like, oh, it's in times 3, or, you know, it's nothing like that. It's not like you add the charges together and multiply it by a number and you're going to get your number. That's not exactly how it works. But you should be able to see the trend in the lattice energy and the electrostatic energy. All right, you guys got questions on that? No? All right, moving on. So this is, you should be able to place the following ionic compounds in order from highest to lowest lattice energies. I'm going to go back, remembering that you have to look at your number of charges here. So why don't you guys just do that? Why don't you do it on your paper? Put them from highest to lowest. Which one has the lowest amount of charges and which one is going to have the highest amount of charges? And remembering that not only do you want to look at your number of charges, but you're also going to have to look at your lattice energy that is higher at the top of the chart and lower as you go down. So which of these compounds only has a negative and a positive? Good, an ACl. And which other one? Rubidium and bromine. So each of these only has a negative and a positive. So that means that they are going to have a lower energy level. Which of these is going to be lower though? The sodium chloride or the rubidium bromine? Rubidium bromine. Why? Because it is lower on the chart. So this one is going to be your very lowest, right? Rubidium bromine, followed by your sodium chlorine. Then look and see again, which one is going to be your next? Which one only has, like, it has 2 negatives and 1 positive? Yep, magnesium chloride and beryllium chloride. Which of those is going to be less? Magnesium chloride. Why, Abby?
Because magnesium is further down than
beryllium. Good job. So we started with rubidium bromide at the bottom, followed by NaCl. Then we're going to do magnesium chloride, beryllium chloride, and why is aluminum oxide at the very top? How many charges are you looking at there? 5 charges. All right, if I gave you a group of elements and asked you to do that again, could you do it?
Yeah.
Possibly. Do you want to ask questions? Do you have questions on that? Okay. All right, so let's talk about naming. We're going to spend 10 minutes talking about naming, then we're going to be done. Remembering naming binary ionic compounds. What does binary mean? 2. So when we have 2 ionic compounds, remembering that we typically have a metal and a nonmetal. So when you are naming, you name your cation, then you write your anion, and you add an IDE on the end. Or you name your metal, and you add the IDE on the end of your nonmetal. So let's practice writing the formula and the name for what we've got on the board. All right, so if we had sodium and sulfur together, so we have Na, which forms a +2 ion, sulfur, which forms a -1 ion. What is my formula going to be? Good job. NaS2. Did Glenn teach you swap and drop? Okay, so you swap and drop your charges, and that's what you get. Now, how do I say this? Name the metal. What is that one? Sodium. Yep. And then you name the nonmetal and add the ID on the end. All right, so how about magnesium and chlorine? Lauren, what's my formula going to be?
Mg1CO2.
Good job. Remembering that we typically don't write the 1, but good job. And how would I say that, Maddie?
Magnesium chloride.
Good job. All right, next, Abby.
Al2O3 aluminum oxide.
Yes, good job. All right, Amy.
Lithium, sodium, and then
Oops.
oxygen, lime.
Yep,
That's lithium nitride.
lithium nitride. Nice job. How confident do you guys feel on that? Are you good? Okay, good. All right, so that is just binary ionic naming, which surely you had like probably pounded into your head last year. Pretty simple. So this is just a chart that's going to show your monoatomic ions and the typical charges on them. Obviously, in the middle of the transition elements, you are going to have to gain or lose. They do not have the same number of charges all the time. The one that I would feel confident saying every time is zinc. Zinc is going to be +2 every time. Other than that, those are just the typical charges. You can see also that they put hydrogen here and here because hydrogen has how many does hydrogen want in its outer shell? It wants 2, right? How many does it have? 1. So it's just as easy to gain or lose an ion. Okay, so these are our metals. They are fairly consistent on our charges. Like you can take it to the bank. That's the charge it's going to be on the, you don't have to worry about it. Zinc is always a +2, and silver is your other. You can count on that being a +1. Your aluminum is always a +3. These are your like guaranteed. These are what they're going to be. Oops. And your I don't know why they have carbon as -4. We're ignoring that. But these in your halogens and halogens in your nitrogen, those are definite ions. Now everything else is kind of left up to chance, and there's exceptions to the rules for the rest of them. Okay, so naming binary ionic compounds. So we're going to start by asking ourselves, do we have a metal and a non-metal? And if the answer to that is yes, we do, we can do what we just said. We can name the metal, then we name the non-metal, and we add the IDE on the end. The question comes when you get into your transition metals. So if your first metal is a transition metal, the first thing you're going to ask yourself is, okay, I got to figure out the charge on that. Now, sometimes they're going to give you the charge. Easy enough, right? You guys know how to do that. You can do it based on just like that. Sometimes they might give you the formula and you have to figure out the charge. Or other times they're going to give you the name. So remembering that transition metals are using the Roman numeral to indicate what charge the ion has. So let's look at the example here of iron 2 chloride. When you see that it says iron 2 chloride, what does that tell you? What does the 2 indicate? The charge of iron. Good job. So when you see iron 2 chloride, that tells you that your iron is a +2 charge and your chlorine is its normal charge. So then you should be able to write your formula from this, right? So what would the formula be for this? Caleb, what would your formula be? FeCO2. Good job. What if you came across and it looked like, Raston, what happened? What if you came across something and it looked like this? What does that tell you the charge on iron is in this compound? Good job. And then how would I write that? It would just be iron 3 chloride. Good job. All right, so you guys should be able to tell the charge or from the name or the formula back and forth either way. Oh, I didn't realize that was my next example. Sweet. Let's do another one. What if I told you that, let's do gold. What if the formula was AuS? So, what's your charge on sulfur? So what is that going to tell you the charge on gold is in this case? Good job. So what's my name going to be? Gold 2 sulfide. I think you guys got that. Yay. I'm not a fan of naming. All right. Are we good on binary ionic compounds with or without transition metals? All right, so transition metals, most have multiple charges. I guess I didn't realize I had this slide. We're going to use the Roman numerals to show the charge. Let's name the one that I have as an example there on the board. TiCl4. So what would the name of that formula, or that formula be? Titanium 4 chloride. Good job. How do I write the Roman numeral 4, Miss Amy?
A little Y.
Good job. IV. Yep. Anybody got questions on any of that? Okay. Here is the list. You guys have this. This is the list of polyatomic ions that I want you to know. So there's 1, 2, 3, 4. You're gonna have to. Okay, so I'll tell you what. How about I make a list of the ones that you definitely should know. So you're gonna need to know ammonium, nitrite, nitrate, carbonate, sulfite, sulfate, hydrogen sulfate, mostly because we do so much sulfuric acid, hydroxide, peroxide, you should know, phosphate. Yeah, I'll make you a list. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 you should know. If you don't know hydroxide after a whole year with Glenn, you're gonna feel this. You guys should know that. After your acid-base unit, come on, you know what hydroxide is. All right, so when we talk about oxoanions, we have 2 different types of anions exist. More oxygen, 8. Less oxygen, 8. So when we have a sulfate ion, SO4, it has more oxygen. Sulfite ion has less oxygen. That's 2 of them that you're going to need to know. SO4, sulfate, SO3, sulfite. As it increases, it's an 8. Imagine that it ate another oxygen, if I remember it. Same thing for nitrate and nitrite. Nitrite only has 2 oxygens, where nitrate has 3 oxygens. So as it goes up, as the oxygen increases, it goes from 8 to 8. Unfortunately, it's not the same number. Like, it's not like NO3 is, yeah. But as it increases, it does. If you have hydrogen, so like if you have HSO4, it's hydrogen sulfate. Or if you have HSO3, it's hydrogen sulfite. Same thing for the nitrite ions. Hydrogen nitrate, hydrogen nitrite. Anytime you add the hydrogen, that's all it does. The common name is bisulfate or bicarbonate. This is probably something that, I don't know if you've heard that, like if you ever do any kind of cooking, bicarbonate, this is baking soda. So, and sometimes like on the older tins, it would say bicarbonate on the baking soda thing, or it says it underneath. Carbonate. Okay, we're just going to go over this quickly as a reminder. When there are 4 forms that exist, we add per and hypo names. So for example, fluorite is our base, FO2. Add an oxygen, it becomes fluorate. So as we increase the oxygen. Add another oxygen, and it becomes perfluorate. Go down, lose an oxygen, hypo, fluorite. Same thing with chlorite. So chlorite, start here, lose an oxygen, it's ClO2. We lose an oxygen, it goes down to hypochlorite. We gain an oxygen, it goes up to chlorate, and we gain another oxygen, and it becomes perchlorate. I don't know if the trending will help you, but that is how the naming works. So if you know fluorate, or you know chlorate, and you know what that polyatomic ion is, from that point, you should be able to figure out fluorite, hypochlorite, or perchlorate. If you just know that one, you understand the trends. We're going to stop here. I'm done for today. All right, tomorrow we'll start with covalent naming, or naming of organic compounds. Naming of molecules. Friendly reminder that your next Mastering Chemistry has been posted. So ACP Chem, Mastering Chemistry, it's 5 due on the 4th, so 2.5 weeks. Yes. I did?
Yeah.
Are you sure I didn't just change it?